Have you ever wondered what an encoder is in digital logic and design? Well, today we're going to break it down for you. An encoder is a combinational circuit, a type of circuit where the output depends solely on the current inputs. Now, you might be familiar with a decoder, which takes a binary code and translates it into an equivalent decimal representation. An encoder, on the other hand, does just the opposite. It takes a set of inputs and converts them into a binary code. So, why would we need an encoder? Well, it's all about efficiency and speed. In the world of digital systems, speed is king, and encoding allows us to transmit data faster, as well as more efficiently. Consider this. Let's say we have a system with 10 inputs. If we were to represent each input individually, we would need 10 separate lines. But if we use an encoder, we can represent these 10 inputs with just 4 lines, thanks to the magic of binary code. This not only saves space, but also makes the system faster, as we have fewer lines to deal with. Encoders are used in various areas of digital systems. For instance, in data transmission, an encoder can take a large set of data and convert it into a binary code, making it easier to transmit over a network. In address encoding, an encoder can take a physical address and convert it into a binary format, which can be used to access memory locations in a computer system. In control systems, encoders can take multiple control signals and convert them into a binary code, making it easier to process. So to sum it all up, an encoder is a crucial component in digital systems. It takes a set of inputs and converts them into a binary code, which can be used for various applications such as data transmission, address encoding, and control systems. Now that you know what an encoder is, let's dive into different types of encoders. There are different types of encoders used in digital design. Let's explore a few of these. First up is the decimal to binary coded decimal, or BCD encoder. This type of encoder converts a decimal digit, ranging from 0 to 9, into a 4-bit binary coded decimal code. It's a handy tool, especially when dealing with decimal data that needs to be processed in a binary system. Next, we have the priority encoder. As its name suggests, this encoder prioritizes multiple inputs. It encodes the highest priority active input into a binary code. This is particularly useful in systems where certain inputs need to take precedence over others. The octal to binary encoder is another interesting type. This encoder converts an octal digit, ranging from 0 to 7, into a 3-bit binary code. As you might imagine, it's a crucial component in systems that work with octal data. Lastly, let's talk about the 8 to 3 binary encoder. This encoder takes one of 8 inputs and encodes it into a 3-bit binary code. It's an example of how encoders can help reduce the complexity of a system by minimizing the number of lines needed to represent data. Now, you might be wondering, what's the common thread among all these encoders? Well, each encoder is essentially a combinational circuit that takes a set of inputs and converts them into a binary code. The specific type of encoder used depends on the nature of the inputs and the binary code required by the system. So whether you're looking to convert decimal digits into binary, prioritize inputs, or minimize the number of lines needed to represent data, there's an encoder for that. These are just a few examples of encoders. Next, we'll look at the basic structure of an encoder. Every encoder has a basic structure that facilitates its operation. This structure is the key to understanding how an encoder works and how it performs its critical role in digital systems. So, let's get into it. At its core, an encoder is made up of multiple input lines and a set of output lines. These output lines represent the binary code that the encoder generates. Now, you might be wondering, how many output lines does an encoder have? Well, the number of output lines is determined by the number of input lines. Let's take a moment to visualize this. Imagine you're looking at a table with rows and columns. Each row represents an input line, and each column represents an output line. The intersection of a row and a column is where the magic happens, where the input is encoded into a binary code. Now, it's important to remember that only one input line should be active at any given time. This is because the encoder's job is to convert the active input into a binary code. If more than one input line is active, the resulting binary code could be ambiguous, and that's not what we want. But what happens when there are more input lines than output lines? Well, that's where the concept of priority comes in. In some encoders, such as a priority encoder, the input lines are prioritized. This means that if more than one input line is active, the encoder will encode the input line with the highest priority. This structure of an encoder, with its multiple input lines and output lines, is what enables it to perform its encoding operation. It's like a well-oiled machine, with each part playing its role to ensure the smooth and efficient conversion of inputs into binary codes. So, there you have it. The basic structure of an encoder is quite simple, but it's this simplicity that allows it to perform complex operations. It's a perfect example of how, in digital systems, even the most basic components can play a crucial role in ensuring efficient data representation and processing. That's the fundamental structure of an encoder. Now let's discuss a common example of an encoder. A common example of an encoder is the 8-to-3 binary encoder. This type of encoder takes 8 inputs, which we'll label from D7 to D0. Now let's imagine that only one of these inputs is active at a time. All the other inputs are inactive or at 0. The task of the encoder is to convert this active input into a 3-bit binary code represented by A2, A1, and A0. To visualize this conversion process, we use something called a truth table. This table lists all possible combinations of the inputs and shows the corresponding binary code output. For example, if D0 is active and all other inputs are inactive, the resulting binary code is 000. If D1 is active, the binary code is 001. As we move up the table, the binary code increases. So when D7 is active, the binary code is 100. This truth table is more than just a list of inputs and outputs. It's a blueprint for how the encoder functions. By looking at the table, we can see a pattern. The binary code output mirrors the position of the active input. That is, when D0 is active, all output bits are 0. When D1 is active, the least significant bit, a 0, is 1. When D2 is active, the second bit, A1, is 1, and so on. This pattern continues until we reach D7, where the most significant bit, A2, is 1. The beauty of the 8-to-3 binary encoder lies in its simplicity and efficiency. It takes a set of 8 inputs and compresses them into a concise 3-bit binary code. This process of encoding not only saves space, but also makes data transmission and processing more efficient. This example illustrates how an encoder works. But how do we implement an encoder circuit? Let's find out. The circuit implementation of an encoder involves a combination of gates. This intricate arrangement allows the encoder to perform its vital task of converting a set of inputs into a binary code representation. Let's delve into this fascinating process. To visualize this, imagine an 8-to-3 binary encoder, which is a common example. This encoder takes 8 inputs and translates them into a 3-bit binary code. How does it achieve this? Through the clever use of AND gates. Each of the 8 inputs, labeled D7 through D0, is connected to an AND gate. These AND gates are the detectives of the circuit. They probe and scrutinize the inputs, diligently identifying which of the lines is active. Once an active line is detected, the AND gate linked to that line springs into action, sending a signal down its associated output line. But what happens when more than one input line is active? This is where the priority mechanism comes into play. In an encoder with this feature, such as a priority encoder, the gates are designed to give precedence to certain inputs over others. This ensures that even when multiple inputs are active, the encoder will always generate a consistent binary code for the highest priority active input. Now let's consider the 8-to-3 binary encoder circuit again. Here, the outputs of the AND gates are connected to an OR gate. This OR gate acts as the conductor of the circuit, orchestrating the outputs from the AND gates into a harmonious binary code. The final result? A 3-bit binary code represented by A2, A1, and a 0 that accurately reflects the active input. This compact binary code is much easier to process and transmit than the original set of inputs, making the encoder an indispensable tool in digital systems. So, from data transmission to address encoding and even control systems, encoders are hard at work behind the scenes, streamlining data and making our digital world run smoothly. Encoders play a key role in digital systems by facilitating efficient data representation and processing. So next time you encounter a binary code, remember that an encoder might have been involved in its creation.